Most of the universe is missing. Everything you can see in the night sky, every star and galaxy, amounts to less than 5% of all existence. The rest is a ghost, an invisible substance whose gravity holds the cosmos together yet completely evades our senses. This is the mystery of the universe's missing mass, a puzzle that invites us to reconsider the very nature of reality. By the end of this journey, you will understand the compelling evidence for this unseen cosmos and the leading ideas that attempt to explain it. We will explore how scientists first encountered this enigma and whether the answer lies in undiscovered particles or a deeper understanding of the laws of physics. What do you believe is truly holding our universe together? The foundations of this cosmic mystery were laid not in deep space, but in a California observatory nearly 100 years ago. Astronomer Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies bound together by gravity. He calculated how much gravity it should take to keep these galaxies from flying apart, based on the amount of visible stars and gas he could observe. The numbers did not add up. The galaxies were moving at astonishing speeds that the gravitational pull from all the visible matter simply could not contain. It was as if an invisible anchor with immense mass was holding the entire cluster together. Zwicky called this unseen substance dunkel materie, or dark matter. For decades, his radical idea was largely overlooked. The scientific community was not ready to accept that most of the universe was made of something they could not see. The turning point came many years later through the meticulous work of astronomer Vera Rubin. She focused not on distant clusters, but on the motion of stars within individual spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, far from the central concentration of mass, should orbit much more slowly than those near the center. Think of our solar system. Mercury, close to the Sun, zips around at a blistering pace, while distant Pluto moves at a relative crawl. Rubin expected to see the same pattern in galaxies. What she found was astonishing. Stars at the very edge of galaxies were orbiting just as fast as those near the core. This was a direct contradiction of gravitational predictions based on visible matter alone. The only possible explanation was that each galaxy was surrounded by a massive, invisible halo of something, a substance exerting a powerful gravitational pull on its stars. This evidence was so compelling that it forced the entire field of astronomy to confront a startling new reality. The universe we see is just a small fraction of the universe that is. This historical journey shows the mystery was not born from a single moment, but from a gradual accumulation of undeniable facts, a puzzle whose pieces pointed to a hidden presence shaping the cosmos from the shadows. The graceful spin of a galaxy holds a secret. If you could trace the orbit of a single star on the outer rim, you would expect it to be a slow, lazy path. After all, the Sun's gravity weakens with distance, so Pluto crawls while Mercury races. This is the simple rule of gravity we learned in school. But when astronomers like Vera Rubin and Kent Ford began meticulously measuring the speeds of stars in spiral galaxies throughout the 1970s, they found something that broke this fundamental rule. The stars far from the glowing center were not moving slowly at all. They were traveling around at speeds nearly identical to those of the stars nestled close to the core. The data painted a graph that became known as a flat rotation curve, a line that refused to dip downward as expected. This was not a small discrepancy. It was a direct and stunning departure from the predicted motion. The only logical conclusion was that these galaxies were not just the collections of stars we see. Each one is embedded within a colossal, invisible sphere of mass, a halo of something that exerts an immense gravitational pull, guiding the outer stars to such incredible velocities. This evidence was so clear, so repeatable across countless galaxies, that it moved the idea of dark matter from a fringe speculation to an unavoidable fact of the cosmos. The missing mass was no longer just a theoretical ghost. It was a measurable presence, its gravitational influence directly felt on the very stars we can see. This revelation from the dance of galaxies forced us to ask, if this unseen substance is everywhere, what other traces has it left across the universe? Einstein's theory of gravity gave us a way to see the invisible. He described space-time as a fabric that massive objects can warp and bend. When light from a distant galaxy travels through this warped space, its path curves, much like a marble rolling across a stretched sheet. This cosmic trick of the light is called gravitational lensing. The result can be multiple, distorted, or magnified images of the same faraway galaxy, a ghostly mirage created by an unseen mass in the foreground. Astronomers use these distorted images as a cosmic scale. By measuring how severely the light is bent, they can calculate exactly how much mass is doing the bending. Time and again, this method reveals a surprising truth. The amount of mass required to create the observed lensing is vastly greater than all the visible stars and gas combined. One of the most compelling examples of this is the Bullet Cluster, a system of two galaxy clusters that have passed through one another. When we look at it, we see a stunning separation. The hot gas from the clusters, which glows in X-rays, was slowed down and lingered in the middle of the encounter. But the maps of total mass, created by measuring gravitational lensing, show that most of the mass sailed right through and now lies on either side, completely detached from the visible matter. This is a direct snapshot of dark matter in action. The substance that interacts via gravity, the true bulk of the mass, clearly parted ways with the ordinary matter that we can see. Gravitational lensing allows us to trace the outline of this unseen presence, to weigh what cannot be seen and confirm its dominant role across the cosmos. If this invisible substance truly forms the backbone of the universe, then its influence must be written into the largest structures of all. The earliest portrait of our universe is painted not in light but in faint heat. This is the cosmic microwave background, a gentle afterglow from the Big Bang that still fills all of space. Within this ancient radiation are tiny temperature differences, small ripples preserved from when the cosmos was in its earliest moments. For many years, satellites like Planck have mapped these patterns with incredible precision, revealing a blueprint of the early universe, and this blueprint holds a crucial secret. The specific arrangement of these warm and cool spots, the way matter began to gather, only makes sense if a specific type of unseen substance was present from the very beginning. The data points overwhelmingly to dark matter, accounting for roughly 27% of everything in the cosmos. Think of those early ripples as seeds. Dark matter's powerful gravity acted as a cosmic framework, a structure that drew ordinary matter together, guiding gas and dust to form the first galaxies and the vast clusters we observe today. Without this unseen component, the detailed pattern imprinted on the cosmic microwave background would be completely inexplicable. This is perhaps the most profound evidence yet, linking the mystery of the missing mass directly to the universe's explosive birth. It tells us that dark matter is not a later addition. It was there at the start, an essential ingredient written into the fundamental recipe of existence. With its role in the grand cosmic architecture now undeniable, a pressing question emerges. If this invisible substance is so fundamental, what could it possibly be made of? So let us take the entire universe and divide it into a pie. The slice representing everything we have ever seen, every star, planet, and nebula, is astonishingly small, a mere 5% of the whole. This is the ordinary atomic matter that forms our world. The next slice, nearly 27% of the cosmic pie, is the invisible substance whose gravitational pull we have been tracing, dark matter. But the largest piece, a staggering 68%, is something else entirely, a force called dark energy, which is driving the accelerating expansion of the cosmos. These numbers are not a guess. They are the result of a cosmic census, a precise accounting built by combining the evidence from the cosmic microwave background, the distribution of galaxies, and the observed speeds of distant supernovae. This standard model of cosmology presents a universe that is profoundly strange, where the familiar world of atoms is a rare exception. The mystery of the missing mass is not a minor accounting error. It is the revelation that the dominant form of matter in the universe is a complete enigma. This cosmic inventory forces the most urgent question in modern physics. If dark matter is not made of atoms, what in the world is it made of? One leading candidate emerges from the deepest theories of physics. Imagine particles that are massive, far heavier than a proton, yet so aloof they barely acknowledge the existence of ordinary matter. They do not emit or absorb light, and they pass through our world and even our own bodies as if it were all a ghostly mirage. These are WIMP, or weakly interacting massive particles. Their only known interactions would be through gravity and the weak nuclear force, the same force responsible for certain types of radioactive decay. This profound shyness is precisely what makes them so difficult to find. The theoretical appeal of WIMP is deeply elegant. They emerge naturally from a framework called supersymmetry, which proposes a hidden, symmetrical partner for every known particle in the standard model. This elegant extension of physics not only solves several theoretical puzzles, but also predicts that vast numbers of these WIMP particles would have been forged in the extreme heat of the Big Bang. The relic density of these ancient particles, the amount that would have survived to the present day, aligns almost perfectly with the measured abundance of dark matter in the cosmos. It is a compelling coincidence that has driven a decades-long search. To catch one of these phantoms, scientists have built incredible traps. Experiments like LUX and Xenon 1T operate in deep underground laboratories, shielded from cosmic rays by a mountain of rock. Their core is a vat of ultra-pure liquid xenon, waiting in the profound silence and cold. The hope is that, on a very rare occasion, a passing WIMP will strike the nucleus of a xenon atom, creating a tiny flash of light and a wisp of electric charge that sensitive instruments can detect. It is like listening for a single, specific grain of sand to drop in a vast, silent cathedral. So far, these detectors have seen nothing but background noise. The profound silence from these exquisitely sensitive experiments is in itself a result. It tells us that if WIMP are out there, they are even more elusive, or their properties are even stranger than our best models predicted. This ongoing null result does not close the door on WIMP, but it has certainly opened a much wider window to other, even more exotic possibilities. Another ghost haunts the theoretical landscape, one that is almost unimaginably light. While WIMP are massive phantoms, actions are their spectral opposite, hypothetical particles trillions of times lighter than an electron. Their origin story lies in a different cosmic puzzle altogether, a subtle asymmetry in the strong nuclear force that holds atomic nuclei together. Physicists realized this problem could be elegantly solved if a new, very light particle existed, and they named it the Axion. It was only later that cosmologists had a stunning realization. The early universe could have produced these particles in absolutely staggering numbers, a dense, coherent wave flowing through all of space. In this scenario, dark matter is not a shower of individual bullets, but more like a silent, pervasive ocean. This fundamental difference in behavior is why Axions would have completely evaded the giant underground traps built to catch WIMP. They simply do not interact with matter in that blunt, nuclear collision way. Instead, their collective presence would be felt as a subtle, oscillating field, its gentle influence contributing to the gravitational fabric of the cosmos. The search for this ethereal substance requires a completely different kind of hunt. One of the most ambitious experiments is the Axion Dark Matter Experiment, or ADMX. It operates not in a deep mine, but in a highly shielded laboratory, and its heart is a powerful magnet cooled to near absolute zero. The idea is brilliant in its conception. Inside this magnetic cavity, scientists hope that a passing action from the galactic halo would, under the right conditions, spontaneously convert into a faint microwave photon. Detecting this specific single photon would be the definitive clue. It is the ultimate exercise in patience, like tuning a cosmic radio across a universe of static, listening for one precise, impossibly quiet note. The existence of Axions would be a beautiful convergence, tying up a loose end in the theory of nuclear forces, while simultaneously providing the invisible mass that shapes the galaxies. That two such wildly different candidates, the heavy WIMP and the ultralight Axion, can both credibly explain the same cosmic observations tells us something profound. The true nature of dark matter may be something so unexpected that it lies entirely beyond our current catalogue of conventional particles. Perhaps the solution to this cosmic riddle was not a new particle at all, but something made of the same ordinary stuff we are. This was the promise of MACHO, a name standing for Massive Astrophysical Compact Halo Objects. The idea was beautifully simple. What if the dark matter halos surrounding galaxies are filled with colossal, dim objects like rogue planets, failed stars known as brown dwarfs, or even ancient black holes? These would be made of protons and neutrons, the same baryonic matter as you and me, but they would emit little to no light, rendering them invisible to our telescopes. For a time, this was a wonderfully elegant and plausible explanation. To test it, astronomers launched ambitious surveys, continuously monitoring the light from millions of stars in neighboring galaxies like the Magellanic Clouds. Their method was to watch for a specific cosmic event called gravitational microlensing. If a massive, dark object like a MACHO were to drift directly between us and a distant star, its gravity would act as a tiny lens, briefly bending and focusing the starlight, causing the star to temporarily flare in brightness before fading back to normal. It is a delicate, fleeting signal, a single star winking at us from across the void. After years of patient observation and the analysis of countless stars, the results were definitive yet disappointing. These microlensing events were simply too rare. While a few MACHO were detected, their total numbers were far too small to account for the immense gravitational pull holding galaxies together. They could explain, at best, only a tiny fraction of the missing mass. This was a critical turning point in the search. The MACHO hypothesis, so appealing in its simplicity, had been observationally ruled out. The universe's dominant form of matter could not be made of atoms. This outcome was in fact a monumental success for the scientific process. It forced a paradigm shift, conclusively demonstrating that the answer must lie in the realm of the truly exotic, in forms of matter that are not just dark, but fundamentally non-baryonic, something completely alien to our everyday experience. With the comfortable, familiar options exhausted, we are pushed to consider possibilities that challenge the very bedrock of physics. But what if the phantom is an illusion? The search for dark matter rests on a fundamental assumption that our current understanding of gravity, perfected by Einstein, is absolute and correct across the entire cosmos. Yet some scientists propose a radically different solution. Perhaps there is no missing mass at all. Maybe the force of gravity itself behaves in unexpected ways over the vast distances of interstellar space. This is the core of modified Newtonian dynamics, or MOND. It suggests that in the extreme weak gravity at the edges of galaxies, where accelerations become incredibly faint, Newton's familiar laws subtly change. The math of MOND can be startlingly simple. It introduces a new, very small acceleration constant and proposes that below this threshold, gravity stops weakening with the square of the distance and instead follows a different rule. When you apply this tweak to the equations governing a galaxy's rotation, something remarkable happens. The need for an invisible halo of dark matter simply vanishes. The flat rotation curves, the very observations that convinced us of dark matter's existence, are perfectly reproduced by the altered pull of gravity itself. This idea turns the mystery inside out. Instead of hunting for a ghostly particle, we are questioning the very fabric of physical law. And in the realm of individual galaxies, MOND has had some notable successes, often predicting galactic motions with impressive accuracy where the standard dark matter model requires careful tuning. Yet for all its elegance on a galactic scale, modified gravity faces its own profound challenges. It struggles to provide a unified explanation for the full suite of evidence. Take the bullet cluster, where the gravitational lensing map clearly separated from the visible matter. A modification of gravity would typically tie the gravitational pull directly to the visible mass, yet here the gravity is strongest where there is almost no light. Explaining this requires adding complex new elements to the theory, making it less elegant. Furthermore, the detailed pattern of the cosmic microwave background, that ancient blueprint of the universe, is exquisitely calibrated by the presence of dark matter. Reproducing that precise pattern with a modified gravity theory alone has proven incredibly difficult, often requiring the introduction of hidden fields or other entities that begin to look suspiciously like a new form of matter. This creates a fascinating philosophical standoff. Do we explain the observations by filling the universe with a new, invisible substance, or do we rewrite the laws of physics that have been so successful everywhere else? The choice is not between a simple and a complex idea, but between two different kinds of complexity. This debate is the engine of science, a vigorous, essential dialogue that forces us to question our most basic assumptions. Whether the final answer lies in a new particle or a new law of physics, the journey to find it is reshaping our understanding of reality itself. The early cosmos was a near-perfectly smooth sea of energy and particles. But within that smoothness, tiny quantum ripples existed, minute variations in density that were the only seeds for all future structure. For these seeds to grow into galaxies, something needed to start the process of collapse, something that could feel gravity's pull but was immune to other disruptive forces. This is where dark matter's unique nature became the universe's great architect. Because it does not interact with light, this mysterious substance was cold, moving slowly and clumping together efficiently under gravity alone. It was free from the intense radiation pressure that buffeted ordinary particles in the universe's first fiery moments. Think of it like this. Imagine trying to build a sandcastle in a storm. Ordinary matter was like dry sand, constantly being blown away, but dark matter was like wet, heavy clay, able to stick together and form the first solid lumps, the foundation upon which everything else could later settle. These early clumps of dark matter created deep gravitational wells, invisible pits in the fabric of space-time. As the universe expanded and cooled, ordinary matter, in the form of hydrogen and helium gas, was inexorably drawn into these wells. It was only then, within these pre-existing dark matter scaffolds, that gas could condense, cool further, and finally ignite into the first stars and galaxies. This narrative is not just a theory. It is vividly demonstrated by some of the most complex computer simulations ever run, like the famous Millennium Run. When scientists program the laws of physics into a virtual universe that includes cold dark matter, the simulation evolves over billions of virtual years to produce a cosmic web of filaments and clusters that looks almost identical to the one we observe with our most powerful telescopes. Run the same simulation without dark matter, and the result is a universe that remains far too smooth and barren, a place devoid of the rich galactic structures we call home. This profound role as cosmic architect makes the hunt for dark matter's true identity more than an abstract puzzle. It is a quest to understand the very framework that made our own existence possible. But how do you find an architect that has never left a visible blueprint? The search now turns from mapping its influence to the audacious attempt to understand the substance itself. Deep beneath the surface, in abandoned mines and under mountains, a silent search is underway. These laboratories are among the cleanest, quietest places on Earth, shielded by thousands of feet of solid rock from the constant rain of cosmic radiation. Their sole purpose is to wait for a whisper from the unknown. At the heart of experiments like LZ and Panda X are immense vats of liquid xenon, purified to an incredible degree and chilled to extreme temperatures. This is the Detector, a target of countless atomic nuclei poised in perfect darkness. The hope is that on a very rare occasion, a particle of dark matter from our galaxy's halo will drift through the tank and gently interact with the nucleus of a xenon atom. This interaction, unimaginably faint, would produce two telltale signatures: a quick flash of scintillation light and a wisp of an electric charge. Catching both signals from the exact same point in the detector is the key to distinguishing a potential dark matter event from the relentless background noise of natural radioactivity. The engineering required to achieve this is staggering. Every component must be crafted from materials selected for their ultra-low radioactivity. The entire system is designed to listen for a sound quieter than a pin drop in a hurricane. After decades of operation and the collective effort of hundreds of scientists, the result has been a profound and telling silence. No definitive signal has emerged. This null result is not a failure, it is data. It tells us with increasing certainty what dark matter is not. It cannot be a WIMP with properties and interaction strengths we once considered most likely. Each new, more sensitive experiment closes another door, placing ever tighter constraints on the possible nature of this elusive substance. This relentless pursuit pushes the very limits of our technology, a testament to human ingenuity in the face of a cosmic riddle. The continued absence of a direct signal on Earth compels us to look upward, to search for the indirect traces this phantom might have left across the sky. While our underground detectors listen in profound silence, other telescopes are tuned to a different kind of signal, one born from transformation. Across the vast halo of our galaxy, dark matter particles might occasionally meet and interact with one another, converting their mass directly into a burst of energy and a shower of secondary particles. This process could produce gamma rays, the most energetic form of light, or flood space with antimatter and neutrinos. We cannot see the interaction itself, but we can search for its brilliant aftermath. This is the promise of indirect detection, a method that turns the entire sky into a giant particle physics experiment. Instruments like the Fermi Gamma Ray Space Telescope have spent years scanning the heavens, meticulously mapping the gamma-ray glow. They have found intriguing anomalies, particularly a puzzling excess of gamma rays emanating from the heart of our Milky Way. This region is expected to have the highest density of dark matter in the galaxy, making it a prime hunting ground. The signal is exactly what many theories predict, a faint, diffuse glow from countless unseen interactions. Yet the story is rarely so clear. The galactic center is also a turbulent place, crowded with pulsars and other astrophysical objects that can produce similar radiation. Disentangling a potential dark matter signal from this cosmic background is one of the great challenges of modern astrophysics. Another compelling clue comes from a precision instrument mounted on the International Space Station, the Alpha Magnetic Spectrometer, or AMS-02. It has measured the flux of cosmic rays with unprecedented accuracy, finding a curious overabundance of positrons, the antimatter counterparts to electrons. This positron excess could be the signature of dark matter particles interacting and producing these antimatter particles, but again, alternative explanations exist. Nearby pulsars, the spinning remnants of ancient stars, can also accelerate particles to incredible speeds and generate positrons. So is the signal from a new form of physics, or simply from a previously misunderstood celestial object? The answer remains elusive. This is the delicate art of indirect detection. It is not about catching the phantom, but about finding its footprints in the snow. Every unexplained gamma-ray glow or anomalous particle flux is a potential clue, a whisper from the dark that must be carefully weighed against all other possibilities. These cosmic messengers, whether they ultimately point to dark matter or to new astrophysical phenomena, are guiding us toward a deeper map of the invisible universe, revealing not just where the missing mass is, but how it might truly behave. A new crack has appeared in our cosmic model, and it points directly back to the missing mass. We call this the Hubble Tension, a stubborn disagreement over how fast the universe is expanding. When we measure the expansion rate using nearby stars and galaxies, we get one number. But when we use the ancient light of the cosmic microwave background to predict what that rate should be today, we get a different, noticeably slower value. The local universe seems to be expanding faster than its own ancient history says it should be. This is not a small measurement error. It is a fundamental discrepancy that suggests something is missing from our story of cosmic evolution. Some physicists are now asking a revolutionary question. Could the properties of dark matter itself hold the key? What if this invisible substance was not entirely passive in the early universe? Perhaps some of it interacted with itself or with radiation in ways we have not yet accounted for, subtly altering the rate of expansion in those first critical moments. Or maybe a fraction of it transformed into other forms of energy, giving the cosmos an extra push. These are not wild guesses, but calculated proposals to make the early and late universes agree. This tension beautifully illustrates that the mystery of dark matter is not a standalone puzzle. It is woven into the very fabric of other cosmological enigmas. A solution to one could very well unravel the other, forcing a revision of our standard model on multiple fronts. This is how science progresses, not in a straight line, but through a web of interconnected mysteries. Each anomaly, each point of tension, illuminates the others. The search for the universe's missing mass is therefore more than a hunt for a particle. It is a journey to reconcile the entire cosmic story, from its first whisper to its present accelerated flight. Where could such a profound reconciliation possibly lead us? There is another contender in this cosmic detective story, one born from the universe's most turbulent beginnings. Imagine not a new particle, but a relic from the very first instant of time, a black hole. Not the kind formed from collapsing stars, but primordial ones, forged in the incredible density and shifting pressures of the Big Bang's earliest moments. In this scenario, dark matter could be a cosmic population of these ancient, compact objects, ranging in size from smaller than an asteroid to more massive than a star. They would be made of ordinary matter, crushed into an extreme state, yet their darkness and isolation would render them nearly invisible, explaining all the gravitational effects without needing any new physics beyond Einstein's gravity. This is an idea that has risen and fallen in popularity for decades, but recent discoveries have given it new life. When the LIGO Observatory first detected gravitational waves from merging black holes, some of the colliding objects were surprisingly heavy, falling into a mass range that is difficult to explain through standard stellar evolution. Could these instead be primordial black holes finally announcing their presence through cosmic collisions? The appeal is clear, offering a solution made from known ingredients, just in an exotic form. Yet the universe always provides its own tests. Searches for these objects through gravitational microlensing have consistently come up short. If the galaxy were filled with planet-sized primordial black holes, they would often pass in front of distant stars, causing them to briefly brighten. Those flares have not been seen in the numbers required. Furthermore, the formation of countless black holes in the early universe would have released tremendous energy, leaving a specific mark on the smooth cosmic microwave background, a mark we simply do not observe. These limits have tightly narrowed the window where primordial black holes could account for all dark matter, perhaps allowing them only in specific, unseen mass ranges. This shows a beautiful cycle in science, where an old, nearly forgotten idea is brought back by new technology, only to be refined and questioned by even newer data. It makes us wonder whether the answer has been hiding in plain sight all along, not as a mysterious particle, but as a fossil from creation itself. With so many paths to explore, from WIMP and Axions to rewritten laws of gravity and now ancient black holes, the persistent lack of a clear signal becomes a profound puzzle in its own right. Why does the universe's dominant form of matter remain so completely, quietly hidden? A single, perfect theory of dark matter should paint the entire cosmos with the same brush. Yet when we look out at the universe, we see a gallery of inconsistencies that no single model has yet been able to frame. This invisible presence must behave in wildly different ways depending on where it lives. This is the diversity problem, and it strikes at the very heart of our search. On the grandest scales, within the immense gravity wells of galaxy clusters, dark matter appears to act as a simple, cold, and collisionless fluid, its gravity sculpting the cosmic web exactly as our best simulations predict. But when we zoom in on the smallest, faintest dwarf galaxies orbiting our own Milky Way, the story completely unravels. Our most trusted supercomputer models, which assume dark matter is inert and non-interacting, produce galaxies with a specific kind of dark matter heart. They predict a steeply rising density, a cusp toward the galactic center. Yet when astronomers measure the motion of stars in these tiny dwarfs, they find the centers are surprisingly fluffy. The dark matter profile appears to be a soft core, not a sharp cusp. This is the Core-Cusp problem, a direct conflict between our premier simulations and direct observation. It is as if the invisible anchor at the center of these small galaxies is far more diffuse than our laws of physics say it should be. Then there is the case of the missing galaxies. Those same sophisticated simulations of cosmic structure formation produce a universe teeming with hundreds of small, dark matter clumps, each one a potential host for a tiny satellite galaxy. But when we look around our own local galactic neighborhood, we find only a few dozen. The vast majority of these predicted satellites are simply not there. This missing satellites problem suggests that dark matter might not clump together on the smallest scales as efficiently as we once believed. Perhaps the particles were moving too fast in the early universe to collapse into such tiny structures, a scenario known as warm dark matter. Or maybe the dark matter does interact with itself through some unknown force, creating a gentle pressure that prevents it from condensing into the smallest, densest halos. These are not minor quibbles. They are fundamental failures of our simplest, most elegant models to describe the real, messy universe we see. A true solution must be a universal solvent, one that can explain the starkly different behavior of dark matter in a massive cluster and a fragile dwarf galaxy simultaneously. This forces theorists to consider far more complex and nuanced physics, painting dark matter not as a simple, passive ghost, but as a substance with a rich, hidden life of its own. Perhaps dark matter is not entirely solitary. The puzzlingly soft centers of dwarf galaxies might be explained if the invisible particles can occasionally interact with each other, not just through gravity, but through some other hidden force. This is the core idea behind self-interacting dark matter, or SIDM. In this scenario, when two dark matter particles pass near each other in the halo of a galaxy, they can gently scatter, transferring energy and momentum. Over vast cosmic timescales, this process acts like a form of cosmic friction. Particles from the dense, cold center are given a slight nudge outward, while particles from the outer regions drift inward. This constant, gentle churning smooths out the sharp central peak that simulations predict, transforming a dense cusp into a much fluffier core. It is a beautifully elegant solution to one of the most persistent small-scale problems in cosmology. The evidence for this is not purely theoretical. Some galaxy clusters show a subtle but telling separation between the dark matter, mapped by gravitational lensing, and the hot gas seen in X-rays. In a major collision, the collisional gas can get stuck in the middle, while the stars, which are mostly collisionless, sail through. If the dark matter also shows a slight offset from the gas, it suggests that it, too, experienced some friction, some self-interaction that slowed its progress. This is precisely what has been observed in a handful of systems, providing a tantalizing clue that dark matter might have a social life after all. Yet the universe demands balance. If dark matter particles interacted too frequently, they would behave more like a fluid, and the beautiful filamentary cosmic web we observe in large-scale surveys would never have formed. The interactions must be just right, strong enough to reshape the cores of small galaxies, but weak enough to leave the grand architecture of the universe untouched. This need for fine-tuning is a challenge, but it also points toward a richer, more complex dark sector. We are no longer just hunting for a single, simple particle. We are being guided toward the possibility of an entire hidden world, with its own forces and perhaps even its own dark light. The ghost that shapes our universe may not be alone in the shadows. Deep within the known family of particles lies a ghost of a ghost. We are already familiar with neutrinos, those elusive, nearly massless particles that stream through the universe, barely interacting with anything. Now imagine a sibling to these phantoms, one that is even more aloof. This is the sterile neutrino, a hypothetical particle that would not interact via any force except gravity. It is deaf to the weak nuclear force, the very channel through which ordinary neutrinos occasionally make their presence known. This profound isolation makes it a compelling candidate for the universe's missing mass. Its existence would be a natural extension of the standard model of particle physics, a right-handed counterpart to the known left-handed neutrinos. The sterile neutrino would be a shadow in the shadows, a component of the dark sector woven from the same theoretical cloth as the particles we already understand. Its primary connection to our world would be through a subtle quantum mechanical mixing with its ordinary cousins, a faint whisper between two realities. This delicate link might be the very thing that gives it away, because if sterile neutrinos exist and if they have a specific mass, they would not be entirely stable. On cosmic timescales, a sterile neutrino could spontaneously transform into an ordinary neutrino and a photon. The energy of that single photon would fall squarely in the X-ray part of the spectrum. This prediction turns the entire sky into a hunting ground. Astronomers have scanned the deep, quiet spaces between galaxy clusters, regions dominated by dark matter, searching for a faint, specific glow at a very precise energy. And they have found something. Several X-ray observatories have reported a faint, unexplained emission line at an energy of around 3.5 kiloelectronvolts. This signal, while not yet confirmed beyond all doubt, is exactly what the transformation of a sterile neutrino with a mass of about 7 kiloelectronvolts would produce. It is a tantalizing hint, a potential fingerprint of the invisible universe. The mass of this candidate is crucial. At this scale, sterile neutrinos would be classified as warm dark matter. They would have been moving at a significant fraction of the speed of light in the early universe, their slight momentum preventing them from collapsing into the very tiniest gravitational wells. This would naturally suppress the formation of the smallest dwarf galaxies, offering an elegant solution to the missing satellites problem that challenges the simplest cold dark matter models. The hunt is now on to verify this signal. Ground-based experiments like CATRIN, which is measuring the mass of ordinary neutrinos with incredible precision, could indirectly reveal clues about their sterile siblings. The next generation of X-ray space telescopes will be designed with the sensitivity to either confirm the mysterious 3.5 kiloelectronvolt line or rule it out entirely. This candidate beautifully bridges the vast scales of cosmology with the minute world of particle physics, showing how an answer to one of our biggest questions might be hiding in the subtle extensions of our smallest theories. As we near the end of our list of potential phantoms, the sheer breadth of the search itself becomes a story. The next 10 years will transform our view of the cosmos. We are on the verge of a data revolution, a cascade of observations from a new generation of instruments designed to corner the phantom. On a mountaintop in Chile, the Vera Rubin Observatory is preparing to open its eye to the sky. Its mission is audacious, to photograph the entire visible sky every few nights for a decade, creating a time-lapse movie of the universe. It will track the subtle distortions of billions of galaxies, mapping the invisible dark matter scaffolding through weak gravitational lensing on an unprecedented scale. This immense survey will reveal the cosmic web in finer detail than ever before, testing our models of structure formation down to the faintest dwarf galaxies. Any discrepancy between what we predict and what we see will be a glaring clue, potentially pointing toward the self-interacting or warm nature of dark matter. Meanwhile, deep underground, the hunt for a direct signal intensifies. Experiments like LUX-ZEPLIN are already pushing the boundaries of sensitivity, but their successors are being designed to be even quieter, even larger. These next-generation detectors will probe regions of parameter space so faint they could finally hear the whisper of a WIMP, or deliver a silence so profound it would effectively close the book on that particular dream. Our view of the ancient universe is also about to get sharper. The CMB S4 project, a coordinated array of ultra-sensitive telescopes at the South Pole and in the Chilean highlands, will study the cosmic microwave background with microscopic precision. It will scour that ancient afterglow for the faintest imprints of primordial gravitational waves and for any subtle signature that could reveal how dark matter behaved in the universe's first moments. In space, two powerful observatories are joining the quest: the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will function as cosmic cartographers of the invisible. By combining incredibly deep and wide surveys of the sky, they will measure the effects of both dark matter and dark energy across cosmic time, tracing the growth of the cosmic web over billions of years. They are designed to find the anomalies, the places where the universe does not behave as our standard model says it should. This is a global endeavor, a symphony of collaboration between ground-based telescopes, underground laboratories, and space-borne observatories. Each instrument plays a different part, from weighing the large-scale structure of the universe to listening for a single nuclear recoil in the dark. Together, they form the most comprehensive search in history, attacking the mystery from every conceivable angle. The promise of the next decade is profound. We are likely to either finally identify the substance that makes up 27% of the cosmos, or we will be confronted with such clean, contradictory data that we are forced to tear down our current model and start anew. Both outcomes would be a monumental leap in understanding. This brings us to a pivotal and humbling question. What if, after all this, we are wrong? What if the answer is not a particle, but something we have not yet even conceived? The search for dark matter is built on an unshakable foundation, the laws of gravity as we understand them. But what if that foundation itself is an illusion? The idea that our entire conception of gravity could be fundamentally incomplete is not a fringe thought, but a profound philosophical challenge. If dark matter does not exist, then the missing mass is not a substance at all, but a symptom. It would signal a flaw in our most basic understanding of how the cosmos operates, a flaw that becomes apparent only on the vast galactic scale. This would require a paradigm shift as monumental as the leap from Newton's clockwork universe to Einstein's relativistic cosmos, a revision that would upend centuries of established science. Such a crisis is not a failure of the scientific process, but its very engine. Historians of science observe that our most significant breakthroughs often emerge from exactly this kind of tension, when stubborn anomalies refuse to fit into the comfortable frameworks of the day. Clinging too tightly to familiar concepts, like an invisible matter we cannot find, can sometimes hinder the revolutionary thinking needed to move forward. If the dark matter hypothesis were to fall, it would not leave a vacuum. It would open a door to entirely new physical theories, perhaps even providing the elusive key to unifying the force of gravity with the quantum world in ways we cannot yet imagine. This possibility serves as a crucial lesson in humility. It reminds us that science is not a collection of unchanging truths, but a dynamic, self-correcting process of continual revision. The certainties of today often become the historical footnotes of tomorrow. Embracing this inherent uncertainty is not a position of weakness, but one of strength. It prepares our minds for whatever the cosmos ultimately reveals, whether it is a new particle or a new law of physics. This grand mystery, therefore, extends far beyond telescopes and particle detectors, touching on how we perceive our own quest for knowledge and our place in a universe that continually defies our expectations. This profound scientific mystery has woven itself into the very fabric of our culture, appearing in novels, blockbuster films, and television series as a powerful symbol of the unknown. The title dark matter has become a shorthand for the invisible forces that shape our lives, a concept that fuels narratives from the adventurous to the philosophical. In the world of Star Trek, it represents a frontier of physics, while in video games and popular books, it often serves as a mysterious energy source or a gateway to other dimensions. This cultural adoption is more than just entertainment. It is a testament to how deeply this cosmic puzzle resonates with our innate curiosity. We are drawn to stories that acknowledge the vast, unseen architecture of reality, and dark matter provides the perfect metaphor for the hidden currents that guide our existence. This widespread fascination creates a powerful feedback loop, generating public excitement and support that directly fuels the ambitious research we see today. When a scientific concept captures the imagination of millions, it becomes easier to fund massive projects, from deep underground laboratories to powerful new space telescopes. More importantly, this cultural moment inspires a child gazing at the stars, a student in a physics class, or a curious viewer to ask the next great question. They see not just a problem to be solved, but a grand story in which they can play a part. The journey to find the universe's missing mass has therefore transcended the pages of academic journals, becoming a shared human endeavor. It connects the most abstract theories of physics to our fundamental desire to understand our place in the cosmos. This story shows that the greatest scientific mysteries do not belong to scientists alone. They become part of our collective narrative, a shared inheritance of wonder that pushes the entire species forward. And this particular mystery is not an isolated island, but a central piece in a much larger puzzle. Its solution intrinsically linked to other cosmic enigmas like the nature of dark energy and the ultimate fate of everything. These two phantoms, dark matter and dark energy, are locked in a cosmic tug-of-war that will decide the fate of everything. One pulls inward with the steady pull of gravity, while the other pushes outward with an unknown force. Their quiet interaction has been unfolding since the dawn of time, shaping the universe on the grandest possible stage. For billions of years, dark matter held the upper hand, its gravitational wells providing the seeds for galaxies to form and cluster together. But around 5 billion years ago, a profound shift occurred. Dark energy began to dominate, and the expansion of the universe, rather than slowing down, started to accelerate. This was the moment the balance of power changed for good. The ultimate destiny of the cosmos now hinges on the precise nature of this mysterious outward push. Will the acceleration continue at its current pace, leading to a distant future where galaxies drift beyond the cosmic horizon, a possibility known as the Big Freeze? Or could dark energy grow stronger over time, eventually overcoming all other forces and separating galaxies, stars, and even the fabric of space-time itself in a final big rip? The answer may be hidden in the very substance we have been searching for. Some of the most compelling theories suggest that dark matter and dark energy are not separate forces, but two expressions of the same unknown physics. Perhaps dark matter can slowly transform, its energy feeding the repulsive force of dark energy and gently altering the expansion rate of the universe over eons. This potential link transforms the mystery of the missing mass from a standalone puzzle into the central piece of a much larger cosmic story. Solving what dark matter is could be the key to understanding not only how the universe was built, but how it will ultimately unfold. Our journey through this mystery has taken us from the spinning edges of galaxies to the first light of the Big Bang, revealing a universe where the visible is merely the tip of a vast, unseen iceberg. We have traced the gravitational signatures of dark matter in the motions of stars, the bending of light, and the ancient blueprint of the cosmos. We have explored the candidates from the elusive WIMP to the spectral action, and considered the revolutionary idea that our laws of gravity themselves may need rethinking. This quest has pushed the limits of our technology and our imagination, sending us deep underground and far out into space. the enduring lesson is one of profound humility and exhilarating possibility. The universe is far stranger and more wonderful than we ever supposed, with 95% of its contents still waiting in the shadows to be discovered. Whether the final answer arrives as a new particle, a new force, or a new law of physics, one thing is certain: the search for the universe's missing mass is far more than a scientific endeavor. It is a fundamental part of the human story, our collective reach to understand the invisible architecture of reality itself. This vast cosmic puzzle is no longer just for the experts with giant telescopes. Thousands of people, from students to retirees, are now joining the search from their own homes. Online platforms like Galaxy Zoo have turned the hunt for dark matter into a global, collaborative effort. Volunteers sift through millions of images of galaxies, their human eyes performing a task that even the most advanced algorithms can struggle with: classifying shapes and looking for the subtle distortions caused by gravitational lensing. This is citizen science in action, and it has led to genuine discoveries, including the identification of entirely new types of galactic structures that might have been missed by automated systems. By opening research to everyone, these projects accelerate the pace of discovery, harnessing the power of collective human curiosity to analyze data on an incredible scale. But the impact runs deeper than just processing power. Every time a volunteer classifies a galaxy, they are learning. They are seeing the evidence for dark matter's gravitational pull firsthand, understanding the scientific process not as a distant abstraction, but as a tangible, participatory act. This fosters a profound public appreciation for the mystery itself, transforming abstract concepts into a shared human experience. The search is enriched by these diverse perspectives, building a global community personally invested in solving one of the greatest cosmic riddles. This collaborative model proves that unraveling the secrets of the universe is a shared human endeavor, a journey that belongs to all of us, and it invites a final, personal reflection. The quest to understand the invisible architecture of reality is ongoing, and everyone, including you, can be a part of it. Our journey through the invisible cosmos has spanned from a single astronomer's radical idea to a global scientific endeavor. We have traced the subtle signatures of dark matter in the swift paths of stars, the bent light of distant galaxies, and the primordial patterns from the universe's first moments. While the leading explanation points to an entirely new form of matter, the persistent appeal of alternatives like modified gravity reminds us that the final answer is not yet written. This is not a closed case, but an ongoing investigation powered by deep underground laboratories, space-based telescopes, and the shared curiosity of people everywhere. The true value of this mystery lies not only in finding a solution, but in how the search itself expands our vision of reality. It teaches us a profound humility, revealing that the familiar world of atoms is a rare exception in a cosmos ruled by the unseen. At the same time, it sparks a thrilling sense of possibility, reminding us that the greatest discoveries often wait just beyond the edge of our current understanding. This quest calls us to think bigger, to question deeper, and to stay open to the universe's next great surprise. I would love to hear your perspective on this cosmic puzzle. What do you believe is the most compelling clue in the search for the missing mass? Share your thoughts in the comments below, and if you enjoyed this deep dive into the universe's hidden architecture, subscribe for more journeys to the frontiers of knowledge. The story of dark matter is still being written, and its next chapter could change everything we know.